When you scrape your plate into the garbage after dinner, it's very easy to just stop thinking about it. Out of sight, out of mind.
Right, yeah. You just tie up the bag and it's someone else's problem.
Exactly. But, I mean, if you zoom out and look at the actual scale of what we throw away, it becomes this entirely different story. We are talking about millions of tons of edible and kitchen waste discarded globally every single year.
It's a staggering amount of waste.
It really is. And, none of it just disappears. It goes straight to landfills where it sets off this whole cascade of environmental issues.
Right, because it just piles up.
Yeah, it piles up. It decomposes anaerobically, meaning without oxygen, basically, which releases massive amounts of methane into the atmosphere. Plus, it creates these terrible odors for the surrounding communities.
Absolutely.
But maybe the most tragic part of this whole cycle is that we are essentially burying incredibly valuable organic resources. I mean, to me, throwing away food waste like that is kind of like throwing away rechargeable batteries when they still have plenty of juice left in them.
That's actually a great way to put it because, we treat organic matter as a nuisance. It's this massive blind spot in municipal management.
Oh, for sure.
I mean, we spend millions of dollars a year figuring out how to bury or burn the foundational building blocks of the Earth biological cycle.
Yeah.
It's kind of wild when you think about it.
Which perfectly brings us to the research we are unpacking in today's deep dive. We've got this fascinating 2022 research article published in the journal Discover Sustainability.
Yes, a really interesting study.
Right. And the title is Prepared Compost from Food Waste, Effectively Increased Onion Production Under Subtropical Conditions. So the premise here is a complete reversal of how we typically view the municipal dustbin.
Exactly.
Instead of treating food waste as this pollution liability, the researchers are looking at it as an unrefined, highly potent fertilizer that's just waiting to be processed. They want to turn it into nutrient-rich compost to drive sustainable agricultural production.
Yep.
So how exactly does this study prove that we can capture that, wasted juice and turn it into a valuable agricultural resource?
Well, the underlying mission of this research is shifting our perspective from waste management to resource recovery. And what's great is that this study isn't just theory.
Right, it's practical.
Exactly. It provides a really concrete, field-tested roadmap for recycling organic waste into high-yield farming. Specifically, it looks at how recycled organic material can revive soil fertility in climates that historically struggle with low crop yields and degraded land.
But, realizing we need an alternative to the way we farm right now is sort of the easy part of the equation, isn't it?
Oh, definitely.
To understand why this team of researchers from Arni University in Himachal Pradesh went through the trouble of designing this highly specific compost recipe, we kind of first need to look at the agricultural dilemma we're currently in. Because modern agriculture has been overwhelmingly dependent on chemical fertilizers for decades now.
And, I mean, for a good reason initially. During the Green Revolution, synthetic chemical fertilizers did exactly what they were engineered to do.
Which was feed everyone, basically.
Right. They delivered a massive immediate boost to crop production, which was absolutely necessary to feed a rapidly growing global population. But the problem is that we are now paying a severe destructive debt for that short-term synthetic boost.
Yeah, and I've always wondered about the actual mechanics of that. People say chemical fertilizers degrade the soil, but I mean, if they're packed with nitrogen and phosphorus, why does the dirt eventually go bad?
It really comes down to the soil microbiome. Healthy soil is essentially this living ecosystem packed with microorganisms, fungi, and bacteria.
Okay.
In a natural cycle, these organisms digest organic matter and slowly convert it into nutrients that the plant roots can actually absorb.
Yeah.
But synthetic fertilizers bypass that entire biological system.
Oh, I see.
Yeah, they feed the plant directly with chemical salts.
Yeah.
So because the soil microbes are no longer getting organic matter to feed on, they just begin to die off.
So it's like the biological engine of the soil just stalls out entirely.
It completely shuts down. You lose soil biodiversity.
Yeah.
And without those microbes naturally cycling nutrients and creating soil structure, the dirt literally loses its ability to hold itself together.
Wow.
It becomes compacted and sterile. You end up with these severe nutrient imbalances where you might have plenty of synthetic nitrogen, but all the trace minerals that plants need for structural health are just gone.
So it's like a sugar rush for the soil, right? Giving this quick burst of energy, but causing a terrible depleted crash later on.
That's exactly what it is. And on top of that, because the soil structure has collapsed, those chemical salts just wash away in the rain, which pollutes local waterways. Add in the skyrocketing costs of manufacturing and importing these synthetic chemicals,
Hmm.
and, well, the entire system becomes inherently unsustainable.
Right.
So organic waste recycling is really being looked at as this urgently needed economic and environmentally friendly alternative to essentially resuscitate our topsoil.
Okay, so to test this resuscitation, the researchers decided to focus on a very specific subject. Allium cepa the humble onion.
Yes, it's one of the world's most vital vegetable crops, both nutritionally and medicinally.
I mean, it's the foundation of almost every cuisine globally, right? But beyond the kitchen, it holds massive economic importance, especially for smallholder farmers.
Huge importance, yeah.
Like, a successful onion crop can sustain a family's livelihood for an entire year. The issue, though, is that in subtropical climates, growing onions is notoriously difficult, isn't it?
Oh, very. The roots are shallow, they require very specific moisture levels, and because the climate is warm and humid all year round, you have intense pest and disease pressure.
Right.
And that pressure is attacking plants that are already struggling in poor, degraded soil.
So why is finding an eco-friendly way to boost onion productivity specifically such a massive win for both a farmer's wallet and, environmental conservation?
Well, if you could solve the productivity problem for a vulnerable, finicky crop like the onion in a tough subtropical climate using local waste, I mean, you prove a massive concept.
Right, a best case scenario.
Exactly. For the farmer, you are replacing highly expensive imported chemical inputs with a resource that is practically free, local food waste. And environmentally, you are rebuilding the soil's biological engine so that the land actually becomes more fertile year after year.
Okay, so how did the researchers actually build this solution? Let's get into the methodology. They basically went to the university boys and girls hostels and collected about 1 quintal, which is 100 kilograms of breakfast, lunch, and dinner leftovers.
Right, just general kitchen scraps and uneaten food.
Which, honestly, 100 kilograms of leftover hostel food sounds like the aftermath of a pretty wild college weekend.
It really does.
But so they took all this waste and they dug this very specific pit. It was 1.52 meters long, 1.22 meters wide, and 1.22 meters deep. They dumped the 100 kilograms of waste in, covered it up, and literally just let it sit for 2 months.
Yep, 2 whole months.
After that, they dried it out on a cement pad, crushed it up, and then mixed it with soil in a 1-to-1 ratio. This produced about 60 to 70 kilograms of usable compost, which they then applied to their experimental farm plots at a rate of 10 tons per hectare.
That's the exact recipe, yeah.
But wait, I'm stuck on something here. I mean, isn't composting just letting garbage rot in the ground? If the whole point is getting this organic matter into the soil to feed those microbes we talked about earlier, why spend 2 months babysitting a covered pit? Why not just till the leftover hostile food directly into the field and let nature do the work where the plants are actually growing?
That's a great question, but doing that would actually destroy the crop.
Really?
Oh, yeah. Throwing raw, decomposing food waste onto an active agricultural field is, well, it's like trying to build a house with lumber that is currently on fire.
Oh, wow.
As raw food decomposes, it triggers this absolute feeding frenzy among the soil bacteria and fungi.
And I assume those bacteria need resources to do all that eating.
Exactly. They require massive amounts of oxygen and nitrogen to break down the complex proteins and carbohydrates in fresh food waste. So they pull all the available oxygen and nitrogen right out of the surrounding soil.
Leaving nothing for the plants.
Exactly. It's called nutrient tie-up, and it completely starves the plants you're trying to grow. Furthermore, this aggressive, rapid decomposition generates a tremendous amount of physical heat.
Oh, I hadn't thought of that.
Yeah, and it releases organic acids that can literally burn the fragile roots of seedlings.
Okay, so the 2-month phase in the pit is really about letting that chaotic, destructive phase happen safely away from the farm.
Precisely. The pit isolates the feeding frenzy. Over those 2 months, the microbes break down the volatile raw food into much simpler, highly stable organic compounds. By the time it's dried, crushed, and applied to the field, it has become stable organic compost. The fire is out, essentially. It will no longer rob the soil of oxygen or nitrogen. Instead, it begins slowly releasing those stored nutrients in a form that the onion's shallow roots can easily absorb without the heat or the acids.
Okay, that makes the experimental design much clearer.
Right.
So they took this stable compost and set up randomized block experiments, running compost-treated plots right next to untreated control plot.
Right, under open field conditions.
Yeah. And they monitored the soil chemistry, the plant morphology, the physiological responses inside the plant, and of course the final crop yield over a growing season, running from day 22 all the way to harvest on day 97.
Using standard analytical and statistical methods throughout the whole process.
Right. So let's look at the immediate impact on the dirt itself, starting with the physicochemical properties. First up is the pH level. The untreated control soil was highly alkaline, sitting at a pH of 9.13.
Very alkaline.
But the compost-treated soil dropped to 8.48. Now, on paper, moving from a 9 to an 8.5 doesn't really sound like a massive leap. Why is that decimal change significant for the plant?
Because soil pH basically dictates whether nutrients are physically available to the plant roots. In highly alkaline soils, like that 9.13 control plot, essential micronutrients like iron, zinc, and manganese undergo a chemical reaction that binds them tightly to the soil particles.
Oh, okay.
It's called nutrient lockout. So the food is technically in the dirt, but the plant roots literally cannot absorb it.
It's like they're starving at a buffet because all the food is locked in a safe.
That's a perfect analogy. The compost acts as a buffer. The organic acids that are slowly released by the stable compost help neutralize that harsh alkalinity, dropping the pH closer to a neutral sweet spot.
And unlocking the safe.
Exactly.
Yeah.
The chemical bonds loosen, and suddenly those locked-up minerals dissolve into the soil's moisture, making them available for the roots to drink up.
Which perfectly explains the next set of metrics they looked at: electrical conductivity, or EC, and total dissolved solids, TDS. The EC went from 9.24 microsiemens per centimeter in the control plot, all the way to 33.33 in the treated soil.
A huge jump.
Yeah, and TDS jumped from 13.000 milligrams per liter to 49.52.
Right, and electrical conductivity is a direct measurement of the soil's ability to conduct an electric current. Pure water doesn't conduct electricity very well, but water full of dissolved salts and minerals definitely does.
Ah, okay.
So a massive spike in EC and TDS means the compost successfully flooded the soil's moisture with a really dense concentration of bioavailable nutrients.
But wait, if we have all these loose dissolved nutrients just floating around in the soil's moisture, doesn't the first heavy rain in a subtropical climate just wash it all away deep into the groundwater?
Well, not if the physical architecture of the soil has been repaired. And that's exactly what the compost does through soil organic matter, or SOM.
Right, the SO numbers were wild.
The researchers found the SOM in the untreated control plot was 24.64%. But in the compost-treated plot, it reached 97.16%.
I mean, that is a staggering difference, 97%.
It is. Organic matter operates structurally like a complex microscopic sponge. It binds individual dirt particles together into larger clusters called aggregates, which creates these porous spaces in the soil.
Okay, so it gives the soil this sponge-like superpower.
Exactly. Because of this new structure, the water holding capacity in the treated plots increased from roughly 19.8% to 29.5%. So the soil sponge holds onto the water, and all those dissolved nutrients suspended in the water tightly enough to prevent them from leaching away during a heavy rain.
But loosely enough that the onion roots can pull them out when they're thirsty.
You've got it. That's exactly how it works. And they saw massive spikes in essential nutrients, too. Phosphorus went from about 28 to 314 kilograms per hectare. Potassium went from 176 up to almost 269. Iron, manganese, copper, and zinc all spiked as well.
And the researchers didn't just rely on observing these physical changes, right? They applied some pretty heavy statistical analysis to the data. Students' t-tests, one-way ANOVA, and two-way ANOVA.
Right. Rigorous statistics.
I think when a lot of people hear terms like analysis of variance or ANOVA, their eyes just kind of glaze over. Why do we actually care about the statistics in a farming experiment?
We care about the statistics because agriculture is full of environmental noise. I mean, in an open field, it is incredibly easy to get a fluke result. Maybe one corner of the plot had slightly better drainage naturally, or, one row just got hit with a bit more wind.
Right, too many variables.
An ANOVA test analyzes the variance in the data to separate that random environmental noise from the actual variable we are testing.
It's a way of checking to make sure the dice aren't loaded.
It confirms causality. The statistical results in this study were significant at a p-value of less than 0.01. That means there is less than a 1% probability that those massive spikes in nutrients were just caused by random environmental flukes. The math basically proves definitively that the hostile food waste compost, the duration of the experiment, and their interaction were the sole catalysts for the transformation in the soil. It gives us absolute confidence in the data.
Okay, so the dirt is structurally repaired, the pH is buffered, and it's holding on to this massive reserve of water and nutrients. how did the actual onion plants respond to this environment?
Very well.
I'll say. The morphological differences, the physical growth, were just night and day. The compost-treated plants reached 47.04 centimeters in height,
Right.
while the control group only hit 24.71 centimeters.
They nearly doubled in size.
Yeah. They grew significantly longer roots, 9.25 centimeters compared to 5.56. They had more leaves, longer leaves, wider leaves, and for the harvestable part, the bulb itself, the treated plants had much thicker necks, and the bulb diameter was 15.18 centimeters compared to just 6.46 in the control.
The bulbs more than doubled in width.
It's incredible. But the physical growth is really just the final result, right? The biological mechanism that allowed the plant to build those massive bulbs is found in the studies section on plant stress physiology.
Exactly. The researchers measured the plant's internal hydration reserves, which is formally called leaf relative water content, or LRWC.
Right, and the treated plants maintained their internal hydration at about 73.4%, while the control group dropped down to 64.4%.
And that gap in internal hydration changes the entire behavior of the plant. A plant breathes and transpires water through these microscopic pores on its leaves called stomata.
Okay.
If the surrounding soil cannot hold water like the degraded control plot, the plant senses an impending drought and goes into a physiological panic. To stop water from evaporating out of its leaves, it slams those stomata shut.
But if the pores are shut to keep the water in, the plant can't take in carbon dioxide from the air, right?
Right, which means photosynthesis completely stops. The plant can no longer convert sunlight into energy. The transportation of nutrients from the roots to the leaves basically grinds to a halt.
Oh, wow.
Yeah, the entire organism shifts from a mode of growth into a mode of basic survival.
That makes the value of the compost's water-holding capacity so much clearer. So because the treated soil acted like a sponge, the roots had a constant, steady supply of moisture. The plants never went into a physiological panic. It's almost like the higher LRWC acted as anti-anxiety medication for the onions.
That's a great way to visualize it because they weren't stressed about finding water, they kept their leaf pores open. Without the stress of drought, they could continuously photosynthesize.
They could focus all their biological energy on just growing massive bulbs.
Exactly. They constantly pulled up that rich supply of dissolved minerals, which the researchers actually verified by finding vastly higher ash content in the treated leaves and bulbs.
Ash content.
Yeah, ash content essentially measures the total accumulated minerals left behind when organic materials burned away. So it proved the plants were constantly feeding. They used that uninterrupted flow of biological energy to build broader leaves, deeper roots, and of course those massive 15-centimeter bulbs.
All of which culminates in the final yield. The untreated control plot, struggling in degraded, highly alkaline soil and constantly battling drought stress, yielded 13.64 tons of onions per hectare.
Right.
But the treatment plot, feeding on composted breakfast and dinner scraps from the university hostels, yielded 32.04 tons per hectare.
Amazing.
That is more than a 130% increase in yield. They didn't just nudge the needle, they fundamentally changed the productive capacity of the land.
And they did it by utilizing a waste product that municipalities normally pay to bury. They rehabilitated the soil's natural mechanics rather than trying to chemically bypass them.
Which brings it all home to you, the listener. Why should you care? Because looking at the broader implications, this research is a highly scalable blueprint for the future. The authors point out that anyone with a kitchen garden can apply this same 1-to-1 compost ratio right now. But on a societal level, this creates a framework for massive, localized economic engines. I mean, you can envision startup companies dedicated to collecting food waste from cafeterias, university hostels, hotels, and corporate campuses, stabilizing it in centralized pits, and then supplying it to regional farmers.
It acts as a dual threat solution. For the smallholder agricultural sector, it slashes the operational costs of buying synthetic fertilizers, which directly improves farmer livelihoods.
Right.
And simultaneously, it diverts thousands of tons of rotting organic matter out of municipal dustbins and landfills, mitigating local pollution and greenhouse gas emissions. The biological loop finally gets closed.
The science clearly shows the mechanics of how we can turn an environmental liability into one of our greatest agricultural assets.
It really does. But, there is one detail mentioned in the study's limitations that provides a vital context for everything we've discussed today.
Oh, what's that?
The researchers noted that due to a lack of logistical support and funds, they were only able to run this field experiment for a single growing season.
Just one season.
Yeah. But consider the data we just walked through. In just one season, using food waste that was composted for barely 2 months, They completely rewrote the physical and chemical profile of the soil, and they more than doubled the crop yield.
It's pretty mind-blowing.
It is. It leaves us with a rather profound question to mull over. What kind of permanent landscape-altering transformation could we achieve in the world's most barren, degraded agricultural regions if we committed to this sustainable cycle not just for a single season, but for a decade?